A serene spiral galaxy drifts in the quiet of space. Now watch it shred into cosmic confetti. What force in nature is powerful enough to devour an entire galaxy? This is the story of the cosmic cannibal. It is not a beast from myth, but a real galaxy called Messier 87, a supergiant with a terrifying secret at its core. By the end, you will understand how this single galaxy rewrites the rules of cosmic survival. We will uncover the ghostly evidence of its past meals and peer into the engine of destruction at its heart. How does a galaxy grow to become the ultimate predator of its kind? Galactic cannibalism is a cosmic act of pure, one-sided consumption. It is not a gentle dance of equals where two galaxies slowly twirl together to form something new. This is a hunt. A larger, more massive galaxy uses its overwhelming gravitational pull to reach out, trap a smaller neighbor, and slowly tear it apart over billions of years. The smaller galaxy does not merge, it is absorbed. Its stars are scattered, its gas is stripped away, and its very identity is erased, becoming nothing more than a meal for a greater power. Think of a solitary shark moving silently through a vast school of fish. The shark does not negotiate or dance, it simply consumes, growing stronger with each encounter. In the dark ocean of space, Messier 87 is that shark. It is the cosmic cannibal, and its appetite is not measured in stars but in entire galaxies. The evidence of its past feasts is written across its form, a ghostly record of destruction on a scale that is almost impossible to comprehend. To find this monster, you must look toward the constellation of Virgo, but not at a single star. You are looking at the heart of the Virgo Cluster, a sprawling city of thousands of galaxies, all bound together by gravity. And at the very center of this immense cosmic metropolis sits its undisputed king, Messier 87. This is not a delicate spiral like our own Milky Way. It is a supergiant elliptical galaxy, a vast, featureless sphere of ancient stars, a glowing amber haze of immense power. Its size is almost incomprehensible. While our galaxy contains a few 100 billion stars, Messier 87 holds the mass of trillions of suns. If the Milky Way were a bustling island nation, Messier 87 would be an entire continent, dark and brooding, dominating the landscape. But its most famous landmark is not a star at all. At its very core lies a shadow, a gravitational pit so deep that not even light can escape. This is M87 star, the supermassive black hole whose image stunned the world in 2019, a fiery ring of light surrounding a perfect circle of darkness. That black hole is the engine of this cosmic beast, a silent, spinning dynamo with the mass of 6.5 billion suns. Its gravity is the reason Messier 87 rules its cluster, the invisible fist that allows it to reach out and consume its neighbors. This galaxy is not just large, it is a gravitational powerhouse, and its history is written in the ghosts of galaxies it has already destroyed. The proof of this cosmic feast is not hidden, it is painted across the galaxy itself in faint, ghostly brushstrokes. When Messier 87 consumes a smaller galaxy, the process is not neat or quick. Over billions of years, the victim stars are pulled away, not all at once, but in a long, drawn-out stellar unraveling. These stars do not simply disappear into the glow of the cannibal. Instead, they are stretched by immense tidal forces into long, faint rivers of light that orbit the giant galaxy. Astronomers call these ghostly structures tidal streams. Imagine slowly pouring a thin stream of glitter into a jar of honey, watching the glitter form delicate, swirling patterns that slowly settle and fade. These streams are the glitter, the last visible traces of a galaxy's structure, now dissolving into the dense honey of Messier 87. In some cases, the disruption creates another kind of phantom, vast concentric shells of stars that ripple outward from the galaxy's center like the rings in a pond after a stone is dropped. These shells are the echoes of a galactic collision frozen in time, For decades, these features were just theoretical predictions, too faint and diffuse for our telescopes to see. But modern observatories, with their ultra-sensitive digital eyes, have now peeled back the bright glare of Messier 87's core to reveal a stunning truth. Surrounding this supergiant galaxy is a complex, tangled web of stellar streams, a sprawling archaeological site of its past violence. One particular survey revealed a vast stream arcing around the galaxy's halo, a river of stars so long it would take light tens of thousands of years to travel from one end to the other. This is not a random scattering of stars, it is a coherent structure, a galactic skeleton. These streams are the cosmic breadcrumbs, and by following their path and measuring the motion of their stars, astronomers can work backwards. They can determine when the meal happened, how massive the victim was, and even the angle of the fatal approach. Each faint river of light is a chapter in the autobiography of a cannibal, a direct line to a moment billions of years ago when a smaller galaxy ceased to be. But the stellar streams are not the only ghosts in this machine. Look deeper into the glowing haze of Messier 87, and you will find another, even more telling clue, a celestial fingerprint left at the scene of the crime. Scattered throughout the galaxy's immense halo are thousands of tiny, dense spheres of light, each one a globular cluster. These are ancient cities of stars, millions of suns bound together in a tight ball, some of the oldest structures in the universe. Our own Milky Way is home to about 150 of them, orbiting like distant moons. Messier 87, however, is surrounded by a staggering swarm of over 12,000. This number is not just large, it is bizarre, an astronomical anomaly that screams something strange happened here. How does one galaxy come to possess nearly 100 times more of these ancient clusters than our own? The answer points directly back to the cannibal's diet. Astronomers theorize that Messier 87 did not form all of these clusters itself. Instead, it stole them. Every dwarf galaxy that fell into its gravitational maw likely brought its own small collection of globular clusters along with it, like cosmic luggage. When the dwarf galaxy was torn apart, its stars were scattered into streams, but its dense, tightly bound globular clusters proved more resilient. They survived the digestion process intact, becoming orphaned clusters now forever orbiting their new, monstrous host. These clusters are the perfect forensic evidence. By studying their chemical composition, astronomers can perform a kind of stellar DNA test. The specific mix of elements in a cluster's stars acts as a birth certificate, revealing where and when it formed. Many of the clusters orbiting Messier 87 have a chemical signature that is completely different from the stars in the galaxy's main body. They are outsiders, immigrants from other galactic systems. Furthermore, by tracking their motions, scientists can trace their paths backward, like rewinding a cosmic film, often linking specific groups of clusters to the same stellar stream, the remains of the same devoured galaxy. So, each of those 12,000 glittering spheres is more than just a beautiful object, it is a trophy, a captured relic from a vanquished foe, now forever part of the cannibal's vast collection, silently testifying to the violent history written in the darkness around Messier 87. Yet this entire history of consumption circles back to a single dark point. At the very heart of Messier 87, anchoring its terrifying gravity, spins the supermassive black hole known as M87 star. Its mass is a number that defies understanding, 6.5 billion times the mass of our own Sun. To grasp that scale, picture our entire solar system from the Sun out to the farthest icy comets. Now imagine cramming 6.5 billion of those complete systems into a single point of darkness. That is the gravitational anchor of this cosmic cannibal. This black hole is not a passive drain, it is the furious engine of the entire galaxy. Its gravity is the invisible hand that governs the dance of billions of stars, the force that binds the galaxy together and gives it the power to reach out and ensnare others. But its influence is far from gentle. As a smaller galaxy spirals in toward Messier 87, it does not simply fall into a smooth, orderly well. It plunges into a zone of chaos. The black hole's gravity creates a turbulent, violent environment, shaking the very fabric of space-time around it. This chaos acts like a cosmic blender, disrupting the orderly structure of the incoming galaxy long before the final act of consumption even begins, making it easier to tear apart. And then there is the jet. From the poles of this spinning black hole, a furious beam of magnetized plasma erupts, a lighthouse beam on a galactic scale. This relativistic jet stretches for 5,000 light-years, a searing column of energy moving at nearly the speed of light. For any galaxy unfortunate enough to wander into its path, this jet is a celestial blowtorch. It can blast away the lifeblood of a galaxy, its clouds of gas and dust, in a process called ram pressure stripping. Imagine a small, fluffy cloud drifting too close to the exhaust of a colossal rocket engine. The cloud wouldn't just be pushed, it would be shredded and scattered into nothingness. That gas is the fuel for future star formation, the raw material of a galaxy's future. By stripping it away, the black hole's jet doesn't just help consume a galaxy. It first ensures the victim is starved and weakened, sealing its fate long before the final gravitational tides do their work. So the black hole is not just the anchor, it is both the butcher and the cook. Its gravity traps the meal, its chaotic environment tenderizes it, and its furious jet can strip away the outer layers, preparing the galaxy for its ultimate absorption into the glowing haze of the cannibal. This galactic biography is written in a language of gravity and time. To read it, astronomers have become cosmic detectives, using the ghostly streams and captured clusters as clues to reconstruct a history of violence spanning billions of years. They feed these clues into powerful computer simulations, virtual universes governed by the immutable laws of physics. By tweaking the variables, the mass of the victim, the angle of approach, the speed of the encounter, they watch as their digital galaxies collide and merge. The goal is simple: to find a simulation that ends with a galaxy looking exactly like Messier 87 does today, surrounded by the same patterns of stellar streams and orphaned clusters. It is a process of reverse engineering, running the film of cosmic destruction backwards to see how the story began. The story they have pieced together is one of relentless, escalating hunger. In the early universe, Messier 87 was likely not the supergiant we see now. It began as a large but not unprecedented elliptical galaxy in a very crowded neighborhood. The Virgo Cluster was a more chaotic place then, with galaxies packed closer together, their orbits more unstable. In this primordial traffic jam, gravitational encounters were frequent and fateful. A smaller dwarf galaxy would stray too close, and Messier 87's gravity would seize it. Over an epoch that makes human history seem like a single blink, the dwarf would be stretched and dissolved, its stars adding to the growing halo of the cannibal. Each meal made Messier 87 more massive. Each addition of mass increased its gravitational reach, making it even more effective at capturing the next slightly larger victim. This is a classic feedback loop of power where success breeds greater success on a cosmic scale. The evidence suggests this has not been a sporadic hobby, but a consistent diet. By counting the distinct stellar streams and grouping the foreign globular clusters, astronomers estimate that Messier 87 has likely consumed hundreds of smaller galaxies over its long life. Some were tiny snacks, mere globular clusters themselves. Others were more substantial feasts, perhaps spiral galaxies 1/10 the Milky Way size, whose delicate structures were utterly erased in the digestive turmoil. The shells and ripples observed around the galaxy are the echoes of the most recent and most massive of these mergers, events so colossal they sent shockwaves of stars oscillating through the cannibal's body, like the ringing of a great bell. This transforms our view from a static portrait to a dynamic, living story. The Messier 87 we see today is not a finished product but a snapshot in an ongoing saga. It is the result of a continuous process of cosmic evolution, where the dominant predator in a crowded cluster grew to dominance through relentless acquisition. It began its life as one among many, and through a billion-year campaign of gravitational conquest, it consumed its way to the top, becoming the central supergiant that now dictates the fate of everything around it. And the most unsettling question this timeline raises is whether the feast is truly over, or if the cosmic cannibal is simply waiting, its immense gravity set, for the next course to wander within reach. From the perspective of a small spiral galaxy, the approach begins with a gentle, almost imperceptible tug. For millions of years, this galaxy, let us call it a small spiral like the Milky Way, has lived a quiet life on the outskirts of the Virgo Cluster. Its stars are born in glowing nebulae, its spiral arms trace elegant patterns through the darkness, but its orbit is a fateful one, slowly bringing it closer to the glowing amber haze at the cluster's heart. The first sign of doom is not a violent collision but a subtle distortion. The immense gravity of Messier 87 reaches out across the void, and it pulls harder on the near side of the spiral than on its far side. This difference in pull, the tidal force, begins to stretch the galaxy like cosmic taffy. Its beautiful, symmetric form starts to warp. The outermost stars, those least bound to the spiral's own core, are the first to be stolen away. They are plucked from their orbits and drawn into long, streaming arcs that point directly toward the cannibal, like rivers of light flowing into a dark sea. This is the galaxy beginning to unravel. As the spiral plunges deeper into the gravitational well, the stretching becomes catastrophic. The entire structure is torqued and twisted. Its delicate arms, once tight coils of gas and young stars, are pulled into grotesque, elongated shapes. Great swaths of its interstellar gas and dust, the raw material for new stars, are ripped away in colossal tidal tails that shimmer faintly against the black. Computer simulations show this process in terrifying detail. The spiral galaxy transforming from a proud, isolated island into a smeared and tortured wreck over hundreds of millions of years. Its identity is being systematically erased. Then comes the final descent. The mangled core of the spiral, now just a ragged clump of its oldest stars, spirals inward toward the chaotic center of Messier 87. Here, in the turbulent space churned by the supermassive black hole and the crowded orbits of trillions of stars, the last vestiges of order are destroyed. The victim's core is shaken apart, its stars scattered like dust in a hurricane. But the galaxy's final act may fuel the very engine that doomed it. If the spiral brought with it a reservoir of gas, that gas does not simply vanish. As it is torn loose and funneled toward the black hole, it swirls into a screaming, superheated disk of material. Some of this stolen fuel may then be catapulted out along the black hole's magnetic poles, adding power to the already terrifying relativistic-jet. In a cruel twist, the victim's remains help energize the weapon that will likely weaken the next galaxy to wander too close. After a billion years, the process is complete. Every star that once belonged to that distinct spiral has been scattered throughout the immense halo of Messier 87. They now orbit anonymously among trillions of others. There are no more spiral arms, no more glowing nurseries of new stars. The vibrant, structured community has been dissolved into a smooth, featureless glow. Artistic renditions of this process capture a haunting beauty in the destruction. The galaxy's last light stretched into ethereal bridges and shells before fading into the amber background. This is not a death by fire, but by dissolution, a slow, gravitational unmaking where a galaxy's story ends not with a bang, but by becoming a single, silent note in a cannibal's chorus. The fate of that spiral was sealed long before it ever felt the first tidal tug. Its doom was written into the very geography of the cosmos. To understand why Messier 87 became such a prolific cannibal, we must zoom out far beyond the galaxy itself to see the crowded, violent metropolis it calls home. This is the Virgo Cluster, a vast gravitational city containing over 2,000 galaxies. Space here is not the empty, lonely void we often imagine. Galaxies are packed relatively close together, separated by distances not much greater than their own sizes. They race around this shared gravitational well at tremendous speeds, thousands of kilometers per second. In this dense, high-speed traffic, close encounters are not rare events. They are an inevitable part of cosmic life. A galaxy's path is constantly being nudged and perturbed by the gravity of its countless neighbors. In such an environment, a smaller galaxy can easily be thrown off a stable orbit and sent on a collision course with a larger one. This is the perfect hunting ground for a predator. Now contrast this with our own quiet celestial neighborhood, the local group. Here we have a few dozen galaxies with vast, empty tracts of space between them. The Milky Way and Andromeda are the two major players on a slow-motion collision course that will take billions of years to culminate. It is a sleepy suburb compared to the bustling, chaotic downtown of the Virgo Cluster. In our suburb, galactic cannibalism happens, but it is a slow, selective process. In the Virgo Cluster, it is a fundamental force of nature, a primary driver of how the entire ecosystem evolves. And at the very center of this swirling metropolis sits Messier 87. Location is everything. Just as debris in a draining sink spirals toward the plug hole, material in a galaxy cluster naturally migrates toward the gravitational center. Messier 87 occupies that central point, the deepest part of the cluster's gravitational well. It is the ultimate sink. Any galaxy that loses orbital energy, whether through a chance encounter or the slow drag of intergalactic gas, will inevitably drift inward over cosmic time, spiraling down toward the dominant giant at the heart of it all. Messier 87 does not need to actively hunt. The very structure of the cluster delivers its meals on a platter, drawn in by the relentless pull of gravity. This process solves a profound cosmic mystery. How do you build the largest, most luminous galaxies in the universe? Galaxies like Messier 87 are not simply born supergiants. They grow to become that way. Astronomers call them brightest cluster galaxies, and they are found sitting like monstrous jewels at the center of virtually every large galaxy cluster we can see. Their immense size and strange, smooth, elliptical shapes are direct products of a lifetime of cannibalism. They are the final products of a billion-year construction project where the central galaxy acts as a gravitational magnet, steadily accreting and assimilating everything that falls into the cluster's core. Each merger adds more stars, more globular clusters, and more dark matter, puffing the galaxy up into the vast, diffuse sphere we observe. Without this mechanism, the existence of such colossal, dominant galaxies would be difficult to explain. So galactic cannibalism is far more than a curious tale of one galaxy's appetite. It is a universal recipe. It is the primary way the universe builds its most massive structures in the densest environments, turning the chaos of crowded space into an engine for creating giants. Messier 87 is not a freak of nature. It is a classic example of a universal rule, writ large and terrifyingly clear. But the stars are only the visible part of the feast. When Messier 87 consumes a galaxy, it is devouring something far more mysterious and massive, something completely invisible. It is absorbing the victim's dark matter halo. To understand this, we must confront the greatest unsolved puzzle in modern cosmology. Every galaxy we see, including our own, is embedded within a vast spherical cloud of dark matter. We cannot see it, touch it, or detect it with any telescope because it does not emit, absorb, or reflect light. It is utterly dark, yet we know it is there because of its overwhelming gravitational influence. The visible stars and gas in a galaxy are like a few Christmas tree lights strung on an enormous, invisible wireframe. The lights are pretty, but the wireframe is what gives the tree its shape and holds everything together. That wireframe is dark matter. It makes up roughly 85% of a galaxy's total mass. So when a galaxy falls into Messier 87, the majority of what is being transferred is not the glittering stars, but this ghostly gravitational scaffolding. This changes the entire scale of the cannibalism. The stellar streams we see are just the luminous tracer, the glitter sprinkled on the surface of a far deeper and darker process. The real prize, the bulk of the mass, is the dark matter halo of the devoured galaxy. As the victim is torn apart, its dark matter halo is also stretched and shredded, but because dark matter particles barely interact with each other or with normal matter, they behave differently. They don't collide and heat up like gas, they simply pass through one another. This means the dark matter from the consumed galaxy disperses more smoothly, blending into the even larger, more massive dark matter halo that already surrounds Messier 87. It is a silent, invisible merger happening in tandem with the violent stellar disruption. So how do you map something you cannot see? Astronomers become detectives of gravity. They carefully measure the motions of the visible tracers, the stars in the tidal streams and the orphaned globular clusters. The speed and direction of these stars are not dictated by the gravity of the visible stars alone. They are whizzing around under the total gravitational pull of everything, with dark matter contributing the dominant force. By charting these motions with extreme precision, scientists can work backwards. They can calculate how much mass must be present to create those orbits and where that mass must be located. It is like watching leaves swirling in a powerful, invisible whirlpool. The pattern of the leaves reveals the shape and strength of the current that moves them. Through this method, the ghostly streams become probes, illuminating the distribution of dark matter in the cannibal's immense halo. Each stream from a different galactic meal cuts through the halo on a different path. This provides a unique, three-dimensional scan of Messier 87's dark matter structure. The data paints a picture of a halo that is not smooth and featureless, but lumpy and complex, still bearing the gravitational scars of past mergers. Some streams may reveal dense clumps of dark matter, the stubborn cores of devoured dwarf galaxies that have not yet fully dissolved. This invisible evidence is crucial because it tells us that galactic cannibalism is not a surface-level event. It is a total restructuring of a galaxy's gravitational soul, where the dominant, unseen component of the universe is also transferred, absorbed, and redistributed in a silent feast that truly shapes the cosmos. The ghostly streams we see are echoes from meals consumed billions of years ago, but the cannibal's table may still be set. Astronomers scanning the halo of Messier 87 have spotted a candidate, a small, faint galaxy that appears to be in the very act of being devoured. This object, often catalogued as a dwarf elliptical, shows the unmistakable signs of a gravitational assault. In detailed images, its shape is not smooth or round. It is stretched and distorted like a ball of clay pulled from two sides. One edge appears brighter and more compact, likely the galaxy's original core, while the opposite side fans out into a faint, diffuse smudge of stars being dragged away by the cannibal's immense tides. This is the moment of unmaking, caught in a single snapshot across millions of light years. The galaxy's velocity tells a confirming story. Precise measurements show it is moving at a speed and on a trajectory that places it deep within the gravitational grip of Messier 87. It is not a distant bystander, it is a captive already spiraling inward on a fatal orbit. Before this encounter, this dwarf galaxy would have been a modest island universe, home to perhaps a few billion ancient stars, a quiet and stable system for most of cosmic history. Now it is a ship caught in a whirlpool, its structure failing. Over the next few 100 million years, its fate is sealed. The stretching will grow more severe. The faint smudge of escaping stars will elongate into a brilliant, doomed river of light, a new tidal stream joining the others in the cannibal's halo. Its core will hold together for a time, a final lump of stellar resistance, before it too is shaken apart and scattered into the glowing haze. This observation is profoundly important because it turns theory into a live observation. We are not just reconstructing ancient history from fossils, we are witnessing the process in its intermediate stages. It confirms that the cannibalism which built Messier 87 is not a relic of a more violent past, it is an ongoing, active force. The monster at the heart of the Virgo cluster is still feeding. This raises a tantalizing and unsettling question. If we could watch this drama play out over cosmic time, what other small galaxies are already on a doomed path, their light already traveling toward us, carrying the news of their own destruction? But this story of cosmic consumption is not confined to a distant supergiant. The echoes of cannibalism resonate right here in our own celestial home. Look up at the serene band of the Milky Way on a clear night, and you are gazing at the legacy of ancient galactic feasts. Our galaxy, too, is a predator, just on a far more modest scale. Astronomers have now mapped the motions of billions of stars with incredible precision. And within that data they have found ghosts, the fossilized remains of smaller galaxies that the Milky Way consumed long ago. One of the most dramatic is known as the Gaia-Enceladus galaxy. This was no tiny dwarf, but a substantial galaxy, perhaps 1/4 the mass of the early Milky Way. Roughly 10 billion years ago, these two young galaxies collided in a colossal merger. The violence of that event stirred the Milky Way's primordial gas, triggering a frenzy of star formation and likely forging the thick disk of older stars we see today. The stars from Gaia-Enceladus did not simply blend in. They retain a distinct chemical fingerprint and move on odd, looping orbits that betray their foreign origin. They are the dispersed population of a conquered kingdom, now forever part of our larger stellar empire, and the feast did not end in the ancient past. Right now, in real time, our galaxy is in the process of consuming another. This is the Sagittarius dwarf spheroidal galaxy, a small satellite that has been orbiting the Milky Way for billions of years. With each close pass, our galaxy's gravity strips away more of its stars, pulling them into long, luminous streams that wrap around the Milky Way like the threads of a great celestial spool. We are witnessing a slow-motion dissection, a live demonstration of the cannibalistic process. The scale, however, is where the comparison becomes humbling. If the Milky Way's consumption of the Sagittarius dwarf is like a wolf steadily pulling apart a rabbit, then Messier 87's galactic feasts are the equivalent of a blue whale swallowing entire schools of tuna whole. Our galaxy is a snack-sized predator in a local pond, while Messier 87 is the cosmic leviathan ruling the deep ocean of its dense cluster. This contrast is profoundly important. It tells us that galactic cannibalism is not a rare or exotic event. It is a fundamental part of how galaxies grow and evolve everywhere. The universe operates on a principle of gravitational hierarchy, where larger structures form by absorbing smaller ones. Whether it is a modest spiral like ours assimilating a few dwarfs, or a supergiant elliptical like Messier 87 devouring hundreds, the underlying recipe is the same. The drama of the cosmic cannibal is simply the most extreme and spectacular version of a story written into the fabric of the cosmos. A story in which even our own galaxy has played both the hunter and, in the deep past, perhaps also the hunted. Our own galaxy has already tasted the role of predator, but its greatest feast is still to come. In the quiet of the local group, a slow-motion cataclysm is unfolding. The Andromeda Galaxy, a faint smudge of light in our night sky, is not a static neighbor. It is on a direct collision course with the Milky Way, rushing toward us at over 250,000 miles per hour. The countdown stands at roughly 4.5 billion years. When that clock runs out, the serene spiral we call home will cease to exist. This will not be a quick, violent crash, but a drawn-out gravitational dance lasting billions of years more. As the two galaxies first approach, their immense gravity will warp each other spectacularly. Long tidal tails of gas and stars will be flung out into the darkness, creating bridges of light between them. Their spiral arms, those elegant structures we see today, will be utterly shredded and distorted into chaotic, beautiful shapes. For a time, the night sky from any surviving planet would be an unimaginable spectacle, filled with the blazing core of Andromeda and rivers of new stars being born in the colliding gas clouds. But the dance is a prelude to a merger. After several close passes, the two galaxies will lose momentum, falling back together and finally coalescing. The result will be a single, massive, elliptical galaxy. Astronomers have already given this future titan a name, Milkdromeda. This is the ultimate local act of cannibalism, where two giants consume each other to become one. And in that moment, the story of Messier 87 becomes a mirror to our own distant future. Milkdromeda will be the new dominant giant in our local group. Its smooth, featureless form, devoid of spiral structure, will be a direct product of that colossal merger, just as Messier 87's shape was forged by its many past meals. It will possess the combined mass of over 1 trillion stars, along with the merged supermassive black holes from both galaxies, now a binary pair orbiting at its heart. This new galaxy will be a gravitational powerhouse. With its immense mass, its reach will extend farther than the Milky Ways or Andromedas ever could alone. The smaller satellite galaxies that currently orbit us, like the Large and Small Magellanic Clouds, will find themselves in a much tighter gravitational grip. Over the eons that follow, Milkdromeda will likely begin to consume them, pulling them in, stretching them into streams, and adding their stars to its growing halo. The process that built Messier 87 in the crowded Virgo Cluster will, on a smaller scale, begin anew right here. Our future galaxy could embark on its own career as a cannibal, slowly devouring the remaining dwarfs in the local group until it stands alone as a solitary supergiant in a now empty neighborhood. This projection ties the grand cosmic process directly to you. The atoms that make up your body, forged in the hearts of stars, are currently part of a spiral galaxy called the Milky Way. In the deep future, those same atoms will be part of a giant elliptical galaxy, a cannibal in its own right. You are living in the early, structured chapter of a story that ends in a smooth, featureless glow. The cosmic cannibalism that seems like a distant, terrifying spectacle is in fact the inevitable fate of our own home in the universe. The faint stellar streams around Messier 87 are 1,000,000 times dimmer than the glow of the galaxy itself. Seeing them requires more than a powerful telescope. It demands a technological revolution. Our window into this cosmic crime scene is built from mirrors in space, lasers on mountaintops, and silicon brains that dream in gravity. The first breakthrough came from a telescope that forever changed our view of the deep sky, the Hubble Space Telescope. Orbiting high above Earth's blurring atmosphere, Hubble's sharp eye could stare for hours, even days, at a single patch of sky near Messier 87. Its sensitive cameras collected every precious photon of light, gradually teasing out the faint, gossamer threads of tidal streams from the overwhelming glare of the cannibal's core. Hubble provided the first detailed maps of this ghostly archaeology, proving these structures were real and not just theoretical ghosts. But to go deeper, we needed a new eye, one sensitive to infrared light. Enter the James Webb Space Telescope. Many of the oldest, most distant stars in these streams glow faintly in the infrared, a light stretched by the expansion of the universe. Webb's immense gold-coated mirror and frigid instruments can detect this ancient warmth, allowing astronomers to see even fainter streams and study the chemical makeup of their stars in exquisite detail. It is like switching from a standard flashlight to a thermal camera in a dark forest, revealing hidden shapes and histories invisible before. Yet space telescopes only give us a static picture, a single frame from a billion-year movie. To understand the action, we need to know how these stars are moving. Are they streaming toward us or away? How fast are they orbiting the cannibal? This is where Earth's great ground-based observatories take over. Instruments like the Very Large Telescope in Chile use a technique called spectroscopy. They take the faint light from a single star in a distant stream and spread it out into a rainbow, a spectrum. Embedded in that rainbow are dark lines, a barcode stamped by the elements in that star's atmosphere. But there is a twist. If the star is moving rapidly toward us, its entire light signature is shifted toward the blue end of the spectrum. If it is fleeing, it shifts toward the red. This Doppler effect, the same phenomenon that changes the pitch of a passing siren, allows astronomers to measure the precise velocity of stars millions of light years away. By doing this for hundreds of stars in a single stream, they can chart its entire orbital path and velocity, reconstructing the dynamics of the ancient merger. Furthermore, that stellar barcode reveals the star's chemical composition, its unique fingerprint. A star rich in iron and heavy elements likely formed later in the universe's history, while one made almost purely of hydrogen and helium is a primordial fossil. By reading these fingerprints, scientists can determine which stars are native to Messier 87 and which are stolen immigrants, definitively linking a stream to a specific devoured galaxy. All this data, the images and the velocities and the chemistry, creates a mountain of clues, but to solve the crime, we need to test our story. This is where supercomputers enter the narrative, performing the ultimate cosmic thought experiment. Astronomers feed the laws of physics, the estimated masses of the cannibal and its victim, and a proposed collision angle into a vast digital universe. Then they press play. The simulation unfolds over virtual billions of years, modeling the gravitational pull of every virtual star and dark matter particle. They watch as their digital galaxy is stretched into streams and shells. The goal is not to get a perfect match on the first try, but to iterate. They adjust the starting conditions, run the simulation again, and compare the final digital halo to the real one observed by Hubble and Webb. It is a process of cosmic tuning, using immense computing power to rewind time and find the single scenario that best explains the faint rivers of light we see today. These simulations are not just videos, they are predictive tools. They might reveal that a particular, oddly shaped stream could only have been formed by a galaxy approaching from a specific direction, a detail that then guides where astronomers point their telescopes next. This powerful feedback loop between observation and simulation is how a faint smudge of light is transformed into a detailed biography of destruction. It is a testament to human ingenuity, a way of touching the untouchable past by combining the reach of our machines with the relentless logic of physics. And it begs a final, profound question. If we can reconstruct the cannibal's past meals with such clarity, what does that tell us about the ultimate fate of all galaxies in a crowded, gravitating universe? That brilliant jet is more than a spectacular light show. It is a direct line to the cannibal's stomach. The superheated plasma screaming from the black hole's poles must come from somewhere, and astronomers now suspect its primary fuel source is the very debris of devoured galaxies. Think of the black hole as a monstrous engine, but one that is often starved. In a giant elliptical galaxy like Messier 87, most of the gas was used up long ago to form its ancient stars, leaving the central black hole in a relatively quiet state, idling on a meager diet of stray interstellar particles. For the jet to ignite with such ferocity, the engine needs a sudden, massive influx of fuel. This is where galactic cannibalism provides the perfect delivery service. When a gas-rich spiral galaxy is torn apart, its most valuable resource is not its stars, but the vast clouds of hydrogen and other gases swirling between them. As the victim is disrupted, these clouds are stripped away, but they do not simply vanish. They become caught in the immense gravitational whirlpool surrounding Messier 87. Some of this stolen gas loses momentum, cools, and spirals inward, cascading down toward the waiting black hole. It forms a screaming, superheated disk of material called an accretion disk, a cosmic whirlpool of matter just outside the point of no return. It is from this disk that the jet is born. The black hole's powerful magnetic fields act like a colossal slingshot, seizing charged particles from the inner edge of the disk and accelerating them to nearly the speed of light, blasting them out into space in those focused, unimaginably powerful beams. So the jet's power is a direct gauge of the black hole's last meal. A sudden surge in the jet's brightness or a change in its structure could signal that a fresh cloud of gas, perhaps from a recently disrupted galaxy, has just reached the inner sanctum, stoking the engine's fire. In this light, the majestic jet is transformed from a static landmark into a dynamic symptom. It is the brilliant, energetic belch of a cosmic predator, a temporary flare-up of activity marking a recent and very large feast. Spectacular images from radio telescopes and the Hubble Space Telescope show the jet's intricate structure, with brilliant knots of energy and vast bubbles of hot gas pushed into the surrounding intergalactic medium. These are not permanent features, but the ongoing echoes of past feeding events. By studying the jet's power and the age of these bubbles, scientists can potentially work backwards, linking specific outbursts to the timing of major galactic mergers revealed by the stellar streams. The jet becomes a second, independent clock, corroborating the story written in starlight. It means that when we look at that famous image of the black hole's shadow ringed with fire, we are not just seeing a dark monster. We are witnessing the active digestive system of a cannibal, a brilliant testament to the fact that even in the silent void, consumption has a visible, spectacular consequence. The fate of a single galaxy reveals a universal law of cosmic construction. Galactic cannibalism is not merely a dramatic spectacle. It is the primary engine that sculpts the largest structures in the universe and dictates the life cycle of galaxies themselves. This process of relentless gravitational acquisition answers one of astronomy's oldest questions: why do galaxies look so different? On one hand, we have vibrant blue spiral galaxies like our Milky Way, flat disks where new stars are constantly being born in swirling clouds of gas and dust. On the other, we have vast red elliptical galaxies like Messier 87, amorphous spheres of ancient dying stars where star formation ceased eons ago. For decades, this divide was a mystery. We now understand that cannibalism is the great transformer, the mechanism that can turn a lively spiral into a quiet red giant. When a spiral galaxy is consumed by a larger one, or when two spirals of similar size merge, the event is catastrophic for their delicate structures. The beautiful, orderly disks are violently shaken and stirred. All that colliding gas, the fuel for future stars, does not simply settle back into a new disk. Instead, the immense turbulence triggers a brief, ferocious burst of star formation, a final stellar fireworks display that uses up the galactic fuel supply in a relatively short cosmic time. Once that gas is either forged into stars or blasted away by shockwaves and black hole jets, the galaxy is left starved. With no fresh gas to condense into new suns, the galaxy's population ages uniformly. The massive, hot, blue stars burn out quickly, leaving behind the longer-lived, cooler, redder stars. The galaxy's color literally shifts from blue to red. Its shape is also irrevocably altered. The merger destroys the orderly rotation of a disk, scattering stars into random, chaotic orbits that form a smooth, featureless ellipsoid, a giant blob of ancient stars. This is the red and dead elliptical galaxy. Messier 87 is the ultimate example of this end state, a galaxy that likely grew through not one, but many such mergers, each one shutting down more star formation and puffing its shape into the colossal sphere we observe today. Its existence and the existence of all brightest cluster galaxies is direct evidence that cannibalism is the universe's preferred method for building giants. But the influence of this process ripples far beyond shape and color. It fundamentally redistributes the building blocks of planets and life. stars are cosmic factories, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron in their cores. When they die, especially in violent supernova explosions, they seed their surroundings with these enriched materials. In a cannibalistic merger, stars from different galaxies, each with their own unique chemical histories, are thrown together. The heavy elements they carry are mixed throughout the new, larger galaxy. This means that in the halo of Messier 87, a star stolen from one devoured galaxy could now orbit next to a star from a completely different victim, each with a distinct chemical signature telling a story of a different stellar nursery. Cannibalism, therefore, is a great blender of cosmic ingredients. It homogenizes the chemical diversity of the universe on a galactic scale, ensuring that the next generation of stars and planets in these giant ellipticals will form from a well-mixed soup of elements. This is why Messier 87 is so much more than a fascinating monster. It is a perfect case study, a living laboratory that demonstrates the dominant evolutionary path for galaxies in dense environments. By decoding its history, we decipher a universal recipe. We learn that the quiet, red giants that dominate the hearts of galaxy clusters were not born that way. They are the products of a dynamic and violent past, the final form of galaxies that grew not by gently collecting gas, but by devouring their neighbors. Their present-day serenity is the calm after a storm of unimaginable duration, a testament to a cosmos where growth is often an act of consumption, and where the largest structures are built from the ruins of countless smaller ones. Yet for all we have reconstructed, the story of the cosmic cannibal remains an unfinished manuscript. Our most powerful tools have illuminated its past, but they also reveal profound gaps in our understanding, mysteries that keep astrophysicists debating late into the night. One of the greatest puzzles is the precise role of that magnificent jet. We know it is powered by the black hole, likely fueled by gas from devoured galaxies, but does it actively assist the cannibalism or hinder it? The jet is a titanic force blasting energy into the surrounding space. Some theorists argue this creates a hostile environment, heating up the gas in the cluster's core and preventing it from cooling and falling into Messier 87, potentially starving the giant of future fuel. Others propose the opposite, that the jet's outward push actually stirs the pot, creating turbulence that disrupts the orbits of smaller galaxies, making them more likely to stumble into the cannibal's gravitational grasp. Is the jet the guardian of the feast or the butcher's cleaver itself? Right now, the data supports both ideas, and untangling this feedback loop is one of the field's most active challenges. Then there is the fate of the victim's own heart. When a spiral galaxy is consumed, what happens to its central supermassive black hole, which might weigh millions of suns? Does it survive the galactic shredding? The leading theory is that it does, at least for a time. As the victim's core is dissolved, its black hole would sink toward the center of Messier 87, drawn by dynamical friction, like a heavy stone sinking through water. It would eventually join the 6.5 billion solar mass monster M87 star in a slow gravitational dance. This would be a binary black hole system, two unimaginable masses orbiting each other in the dark heart of the cannibal. Such a pairing would warp space-time itself, sending out ripples known as gravitational waves. But does this dance end in a merger? The process of two supermassive black holes finally coalescing is fraught with theoretical hurdles. They may stall, entering what astronomers call the final parsec problem, where they need to shed orbital energy to spiral the last critical distance, and it is unclear if the stellar environment provides enough friction. So, is M87 star actually a composite beast, the silent product of multiple black hole mergers from all its past meals? Or does it keep a collection of smaller black holes trapped in eternal orbit around it, a hidden court of dark monarchs? Our current telescopes cannot peer into that central chaos to see. This leads to the ultimate genealogical question: how many generations of mergers actually built this giant? We see the streams and the shells, the evidence of many meals, but was there a single defining feast that made it a supergiant, or was it a steady diet of hundreds of small snacks? Competing simulations tell different stories. One school of thought suggests Messier 87 grew through a few major mergers with other large galaxies early in its history, events so violent they completely reshaped it and shut down star formation in one go. Another argues for a more gradual, hierarchical buildup, a relentless accumulation of dwarf galaxies over nearly the entire age of the universe. The chemical fingerprints of the stars in its halo hold the answer, but reading that record is painstaking work. Each theory predicts a different pattern of elemental abundances and stellar ages scattered through the halo. Astronomers are now using the James Webb Space Telescope and ground-based spectrographs to take a galactic census, star by star, hoping their chemical DNA will reveal whether the cannibal's lineage is one of royal marriages or of endless petty conquests. These are not just academic debates, they are fundamental to predicting the future of galaxies everywhere. If the jet stifles growth, then perhaps Messier 87 is nearing the end of its reign, its future meals limited. If black holes from victims merge efficiently, then the engine at its core will grow even more powerful with each conquest. And if growth is primarily gradual, then the cannibal may still be quietly feeding, its greatest consumption yet to come. Every new observation adds a piece to this puzzle, but also reveals how much of the picture is still missing. The story of the cosmic cannibal is not a closed book on a shelf. It is a living document, its next chapters being written in the faint light of ancient streams and the silent mathematics of gravity, waiting for our next generation of telescopes to turn the page. The ghostly evidence around Messier 87 is not a cosmic anomaly but a common signature. Our universe is filled with galactic predators, each with its own unique scars from a lifetime of consumption. A mere 45 million light-years away, in the constellation Centaurus, lies another famous cannibal, Centaurus A. At first glance, it appears bizarre, a massive elliptical galaxy bizarrely slashed across its middle by a thick, dark lane of dust. This is not a natural feature of an elliptical galaxy, which is typically a smooth, dust-free sphere of old stars. That dramatic dust lane is the mangled corpse of a spiral galaxy it devoured, likely within the last few 100 million years. The spiral's gas and dust were torn apart and captured, now forming a ragged band that obscures the cannibal's brilliant core. Jets of radio waves scream from its central black hole, hinting at the violent feast that recently fueled its engine. Centaurus is a cannibal caught with the evidence still fresh, its last meal not yet fully digested. Travel farther to the Virgo Cluster, and you will find NGC 1316, another colossal elliptical. Its surface is not smooth but textured with faint concentric ripples like the surface of a pond disturbed by multiple stones. These are the shell structures predicted by theory, the frozen ripples from not one but several galactic mergers. Each shell represents a distinct act of consumption, a moment when a smaller galaxy was pulled in and its stars sent oscillating through the giant's halo. Studying NGC 1316 is like reading a geological stratum of violence, with each layer recording a different epoch of its predatory past. How do these other predators compare to the king in Virgo? In scale, Messier 87 remains the supreme example. Centaurus A and NGC 1316 are massive, but they are not the central, governing giants of their respective clusters in the same way. Messier 87's position at the absolute gravitational bottom of the Virgo Cluster gave it a consistent delivery of galactic material, allowing it to grow to truly supergiant proportions. Its methods, however, are universal. The tidal streams, the shell structures, the captured globular clusters, and the active jets are all recurring motifs in the story of galactic cannibalism. The differences lie in the details of the last meal. Centaurus swallowed a particularly gas-rich spiral, leaving that iconic dust lane. NGC 1316 seems to have consumed several gas-poor galaxies, leaving mainly stellar shells. Messier 87's history appears to be a complex blend of both, a layered chronicle of varied feasts. This gallery of predators reinforces a profound and humbling cosmic truth. In the crowded cities of galaxy clusters, cannibalism is not a rare catastrophe. It is an expected phase of life. It is a fundamental mechanism of growth and change, as natural as rainfall shaping a mountain. Galaxies are not isolated islands, forever destined to spin in solitude. They are social creatures bound by gravity, and in dense environments, interactions are inevitable. The largest galaxies naturally evolve into gravitational sinks, growing by absorbing those that wander too close. Messier 87 is not a monster, it is an archetype. It is simply the most extreme and well-studied specimen we have, a perfect laboratory that has taught us to recognize the same story written in fainter ink across the skies. Its dominance shows us the ultimate endpoint of this process, a future that may await the merged remnants of our own Milky Way and Andromeda billions of years from now. So when you look at the serene haze of a distant elliptical galaxy, remember you are likely not looking at a peaceful elder, but at a retired titan. Its smooth glow the final, quiet testament to a violent and hungry youth spent devouring its neighbors. This predatory growth reaches far beyond a single galaxy's halo. The cannibalism that built Messier 87 is the same force that sculpts the largest structures in the observable universe. To see this, you must zoom out until individual galaxies blur into a faint, glowing haze. You are now looking at the architecture of a galaxy cluster itself, a vast metropolis of dark matter and hot gas where thousands of galaxies are mere inhabitants. At the heart of this metropolis, the supergiant-galaxy acts as the ultimate gravitational anchor. Its immense mass, accumulated through eons of consumption, creates the deepest part of the cluster's gravitational well. Think of a massive boulder resting in a valley, its weight defining the valley's very shape and determining how everything else within it will settle. Messier 87 is that boulder for the Virgo Cluster. Its relentless growth through cannibalism does not just change itself, it dictates the physics of its entire environment. This influence is written in a medium we cannot see with our eyes, a searing ocean of plasma that fills the space between galaxies. When telescopes sensitive to X-ray light peer at the Virgo Cluster, they reveal a stunning sight, not points of light but a vast diffuse glow. This is the cluster's intracluster medium, a superheated gas with temperatures reaching millions of degrees. This gas did not simply appear, it was largely pulled out of galaxies themselves over billions of years, often during the violent process of mergers and cannibalism. As galaxies interact and are torn apart, their cold gas is stripped away, heated by shocks, and added to this communal reservoir. The gravitational anchor at the center, Messier 87, plays a crucial role in this ecosystem. Its gravity helps confine this immense, hot atmosphere, preventing it from simply drifting away into the void. The energy from its supermassive black hole's jet then pumps into this gas, creating bubbles and ripples that redistribute heat, effectively acting as a cosmic thermostat for the entire cluster. This feedback loop, governed by the central cannibal, regulates whether gas can cool and flow inward to form new stars or whether it remains hot and quiescent, directly influencing the fate of every other galaxy in the neighborhood. On the grandest scale, this process is woven into the cosmic web, the vast filamentary network of dark matter that forms the skeleton of the universe. Galaxy clusters are the dense knots where these filaments intersect. The cannibalistic growth of the brightest cluster galaxy is a natural consequence of this geography. Dark matter flows along these invisible filaments, pulling normal matter, gas, and galaxies with it toward the cluster's core. The central galaxy, sitting at the node of this cosmic river system, receives a continuous delivery of material. Its cannibalism is simply the visible stellar manifestation of this larger, darker accretion process. Each devoured galaxy represents a stream of dark matter and stars that once traveled along a filament, finally reaching its destination. In this way, the local act of destruction you see in the tidal streams around Messier 87 is not an isolated event. It is an integral, necessary part of how the universe's largest structures assemble themselves. The cannibal is both a product and a shaper of its environment, a giant grown from the universe's underlying architecture, now using its accumulated might to govern the continued evolution of its corner of the cosmos. This reveals a profound symmetry where the same force that tears a single galaxy apart is also the force that builds and maintains the greatest cities of light and matter in existence. These digital universes begin with a single, elegant command: let there be gravity. Physicists do not write stories, they write equations. They translate the fundamental laws of the cosmos, the same mathematics that describes how an apple falls and how planets orbit, into lines of computer code. This code becomes the rulebook for a virtual cosmos, governing every particle within it. But to simulate a galactic cannibal like Messier 87, gravity alone is not enough. The recipe must include three profound ingredients. First, the dominant but invisible hand of dark matter, whose particles are programmed to feel only gravity, flowing and clumping to form the cosmic scaffolding. Second, the ordinary baryonic matter, the gas that can heat, cool, condense, and eventually ignite into virtual stars. And third, the furious feedback from those stars and the supermassive black holes they form, whose explosive deaths and powerful jets inject energy back into the system, preventing runaway star formation. This triad of forces, gravity, gas physics, and feedback, is woven into a simulation with trillions of digital particles, each representing a swarm of stars or a cloud of dark matter. Then the scientists set the initial conditions, a virtual Virgo cluster in its infancy, and press play. On a screen, what unfolds over the next few days of computation is a breathtaking time lapse of billions of years. You watch as dark matter halos coalesce from the primordial soup, as gas funnels into their centers and sparks into the first galaxies. You see these infant galaxies, pulled by their own coded gravity, begin to drift together to cluster. And at the heart of this digital metropolis, one galaxy begins to pull ahead. It is not predetermined to be the cannibal, it earns that title through the emergent logic of the simulation. As smaller galaxies spiral toward it, you witness the entire process of unmaking in exquisite, terrible detail. You see the victim stars stretched into those exact same luminous streams we observe around the real Messier 87. You watch its dark matter halo smear and blend into the predators. You can even track the stolen gas as it spirals down to fuel a virtual supermassive black hole, triggering a brilliant jet that pushes back on the surrounding intergalactic medium. Projects like the Illustris TNG simulation have produced some of the most stunning visualizations of this cosmic drama. In these renders, space becomes a swirling canvas of light and shadow. Two spiral galaxies, each a delicate whirlpool of blue star-forming regions and dark dust lanes, approach each other. Their first gravitational embrace is beautiful and destructive, pulling long, shimmering tidal tails of stars out into the darkness. Over countless frames, their distinct shapes dissolve into a chaotic, glowing mess, which then settles, smooths, and puffs out into the familiar, featureless amber glow of an elliptical giant. It is the birth of a cannibal recorded not by a telescope but by a supercomputer's dream. Yet these are not just spectacular movies, they are rigorous scientific instruments. The true power of a simulation lies in its ability to be tested. Astronomers run their virtual universe, then they pause it at the present cosmic epoch, 13.8 billion years after the Big Bang. They then generate a synthetic observation, a fake image or dataset of their simulated cannibal galaxy and its surroundings. They ask, does our virtual Messier 87 have 12,000 globular clusters? Does it show the same pattern of faint stellar shells and streams? Does the temperature and distribution of hot gas around it, as seen in X-rays, match the real observations from the Chandra telescope? If the simulation fails these tests, it is not a failure of nature but of the recipe. The physicists must go back, tweak the strength of black hole feedback or the efficiency of star formation, and run the entire universe again. This process of prediction, comparison, and refinement is how these digital laboratories unlock the details we cannot observe directly. They allow us to rewind a single stellar stream and identify the precise mass and approach angle of the galaxy that created it. They let us fast forward to see if a currently observed dwarf on a suspicious orbit is truly destined for destruction. By finding the simulation that perfectly mirrors reality, we gain confidence that the physics coded within it reflects the true physics of our universe. In this way, the ghostly streams around Messier 87 are not just fossils, they are calibration points. Each one helps tune the simulation, making it a more accurate time machine. And with each iteration, our digital apocalypse becomes a clearer window into the real one, revealing that the cannibal story is written not in stars alone, but in the immutable, coded logic of gravity itself. The stars from those devoured galaxies are not gone. They have simply been reassigned. This cosmic cannibalism forces us to confront a profound philosophical truth about the universe, that destruction and creation are not opposites but partners in a single, endless dance. The violent merger that tears a galaxy apart is the same event that seeds the future. When two galaxies collide, the chaos does more than just scatter old stars. It compresses vast clouds of stolen gas, triggering a firestorm of new star birth. The heavy elements forged in the hearts of those ancient stars, the carbon, oxygen, and iron, are churned back into the cosmic stew. These are the very elements that will one day coalesce into rocky planets, oceans, and perhaps life. The cannibal does not erase, it recycles. The atoms in your hand right now, the iron in your blood, were likely forged in a star that died billions of years ago in a galaxy that no longer exists. Those atoms were then scattered by some violent event, perhaps a supernova or even a galactic collision, before they eventually found their way into a nebula, a new star, and finally you. Your existence is a direct product of cosmic destruction. This mirrors the most fundamental cycles we know on Earth. A forest fire is a terrifying force of annihilation, yet it clears the way for new growth, returning nutrients to the soil. The death of a massive star, a supernova, is the ultimate act of self-destruction, yet it is the only way to forge elements heavier than iron and blast them across space to become part of new worlds. The universe operates on this principle of creative destruction at every scale. What we witness in the serene halo of Messier 87 is not a graveyard but a nursery in disguise. It is a galactic ecosystem where the end of one story provides the raw material for the next. This transforms our view from one of horror to one of awe. The cosmic cannibal is not a mindless monster. It is a gardener on a billion-year timeline, tilling the stellar soil and sowing the seeds for futures we can scarcely imagine. It asks us to expand our sense of time and consequence, to see that in the grand tapestry of the cosmos, an ending is very often just a different kind of beginning. But what if the cannibal's next meal was a galaxy like our own? The serene spiral of the Milky Way, with its billions of potential worlds, drifting into the gravitational well of a monster like Messier 87. For any life existing in that doomed galaxy, the end would not come with a sudden, fiery crash, but with a slow, cosmic sterilization. The concept of a galactic habitable zone suggests that life requires more than just a planet in a star's Goldilocks zone. It needs a stable galactic neighborhood away from the violent core. A galaxy falling prey to a cannibal is thrown into the ultimate instability. As the victim's structure is torn apart, the first threat is radiation. the cannibal's central black hole, fueled by the incoming torrent of gas, would erupt in furious outbursts. The relativistic-jet, that searing column of energy, would sweep across vast tracts of space. Any planetary system caught in its path would be scoured by intense X-rays and gamma rays, stripping atmospheres and baking surfaces sterile in a celestial flash. Even planets far from the jet's direct line of fire would face a rising background of deadly radiation from the hyperactive core, a constant rising drizzle of poison that could collapse ecosystems over millennia. The violence is not confined to the center. As the galaxy's orderly rotation is shattered, stellar orbits become chaotic highways. The risk of catastrophic stellar close encounters or even direct collisions increases exponentially. Imagine our solar system, a delicate clockwork of orbits, suddenly jostled by the gravitational wake of a passing star. Planets could be flung into the cold depths of interstellar space or hurled into their own sun. The once predictable sky would become a chaotic pinball machine of brilliant passing suns, each one a potential agent of orbital chaos. For any civilization gazing upward, the heavens would literally be falling apart. The beautiful spiral arms, those stellar nurseries, would be twisted into grotesque shapes, their gas clouds compressed not into gentle cradles for new stars, but into violent, short-lived bursts that flood space with lethal radiation from massive, quickly dying stars. The galactic habitable zone, that quiet suburban ring of stability, would vanish entirely, replaced by a galaxy-wide zone of danger. Yet, in the grand paradox of cosmic cycles, this apocalypse could also plant the seeds for distant futures. The same colossal compression of gas that creates deadly radiation bursts also forges new generations of stars and planets, enriched with the heavy elements scattered by the violence. In the long, quiet aftermath, after the cannibal has digested its meal and its black hole engine calms, new solar systems will condense from the recycled debris. These new worlds will be built from atoms that were once part of a doomed spiral galaxy, now mixed thoroughly with material from the cannibal itself. They will orbit stars born from the ashes of the catastrophe. The iron in their cores and the carbon in their soils will tell a story of both destruction and rebirth. For life to arise there, however, it would need to wait. It would require billions of years of quiet stability for evolution to begin its slow work in a new galaxy that has itself become a quieter, more settled giant. So the answer is a matter of perspective and time. For any living world caught in the act, cannibalism is an existential terror, a guarantee of biological extinction. But for the universe itself, it is simply a phase change, a turbulent but necessary step in the endless recycling of material from one form to another, where the end of one story of life might, after an almost unimaginable pause, make the next story possible. The faint streams we see today are just the beginning of the story. Our view of the cannibal is about to become exponentially sharper, thanks to a new generation of cosmic observatories poised to rewrite the map of the sky. The first is a revolutionary eye on a mountaintop in Chile, the Vera C. Rubin Observatory. When its survey begins, it will not merely look at the sky, it will watch it night after night for a decade with a camera the size of a small car. This relentless scan will create the deepest, widest movie of the universe ever made. For Messier 87, this means a profound shift from snapshot to motion picture. The observatory's immense light-gathering power will detect stellar streams 100 times fainter than those we can see now, revealing the complete, tangled web of the cannibal's past meals. More importantly, by measuring the subtle motions of stars in those streams over years, we will not just see the ghosts, we will watch them move. We will trace their orbital paths with precision, turning static fossils into dynamic timelines. This could allow us to date each act of consumption with unprecedented accuracy, sequencing the cannibal's entire dietary history. It might even catch the earliest, faintest distortions of a new galaxy just beginning to fall in, giving us a real-time alert for the cannibal's next meal. While Rubin scans the broad canvas, another mission will focus its gaze with exquisite detail on the cannibal's halo. The Nancy Grace Roman Space Telescope, NAS, a next great observatory, will possess a field of view 100 times larger than Hubble's but with the same crystal-clear resolution. This combination is perfect for a target like Messier 87, which sprawls across a large patch of sky. Roman will conduct a stellar census of the cannibal's outer realms, pinpointing and analyzing millions of individual stars within those faint streams and shells. It will measure their chemical compositions en masse, performing DNA tests on entire populations of stolen stars at once. This will let us group streams that came from the same devoured galaxy with certainty, and perhaps even identify distinct families of stars from several different victims that arrived in a single colossal merger event. Roman's data will transform the halo from a blur of ancient light into a detailed genealogical chart, showing exactly which stars are native and which are immigrants, and from which galactic lineages they descended. And then, of course, there is the beast at the heart of it all, M87 star. The first historic image was just a single frame. The next goal is a movie. Plans are already underway for a next-generation Event Horizon telescope, incorporating new radio dishes in space and on the ground to create an even more enormous virtual telescope. The aim is to capture not just a sharper image, but multiple images over time, creating a time-lapse of the black hole's immediate environment. We could see the fiery accretion disk not as a static ring, but as a swirling, dynamic maelstrom. We might witness blobs of superheated plasma, perhaps gas ripped from a recent galactic snack, as they orbit and finally vanish past the point of no return. Watching how the black hole's shadow and its ring of light change and flicker will tell us about the rate at which it is being fed, offering a direct gauge of the cannibal's present-day appetite. Is the engine idling, or is it actively digesting? The flicker of that dark shadow may hold the answer. These missions represent more than technological leaps. They are chapters waiting to be written in the biography of a cosmic giant. Each new stream discovered by Rubin, each stellar family tree mapped by Roman, and each flicker from the dark heart of M87 star will add lines to a story we have only begun to read. The evidence gathered will feed our supercomputer simulations, making them more accurate and predictive than ever. We are on the verge of moving from reconstructing the cannibal's past to potentially forecasting its future. What we learn will not just be about one supergiant in Virgo, but about the fundamental recipe of growth for all massive galaxies across time. The detective story that began with a faint smear of light in a telescope eyepiece is accelerating toward revelations we can scarcely predict, proving that the universe's greatest monsters still have secrets to surrender. Its biography is now complete, written in the language of light and gravity. We have traced the life of this cosmic titan from its origins to its reign, following the evidence it left behind like a trail of celestial breadcrumbs. The faint stellar streams arcing through its halo are the final, dissolving signatures of galaxies it devoured, each one a river of light marking a separate act of consumption. The staggering swarm of over 12,000 globular clusters are the captured trophies from those same feasts, dense cities of stars that survived the digestion to orbit their monstrous new host. At the very center, the supermassive black hole M87 star acts as the relentless engine of this entire system. Its gravity the trap and its furious jet a tool that may both prepare and regulate its meals. And none of this would have been possible without the crowded, chaotic metropolis of the Virgo Cluster, a dense gravitational city that delivered countless galaxies into the cannibal's waiting grasp over billions of years. This is the comprehensive picture, a story of transformation. Messier 87 did not begin as a supergiant. It started as one galaxy among many, but through a relentless billion-year campaign of gravitational conquest, it consumed its way to the top. Each meal made it more massive. Each addition of mass increased its reach, creating a feedback loop of power that sculpted the serene giant we see today. Its present calm is the quiet after a storm of unimaginable duration. Its smooth glow the final testament to a violent and hungry youth spent devouring its neighbors. The evidence, the process, and the immense scale all tell the same unified story of a cosmos where growth is often an act of consumption, and where the largest structures are built from the ruins of countless smaller ones. The story of Messier 87 is not an isolated tale, but a single verse in a universal epic. Zoom out from the cannibal's glowing halo, and its entire domain, the Virgo Cluster, resolves into a delicate smudge of light, a city of 1,000 galaxies. Pull back further still, and that cluster becomes one tiny knot in a sprawling, glittering web, the large-scale structure of the universe itself. This is the true context. Every filament of that cosmic web, every dense cluster node, hums with the same gravitational logic that built the monster in Virgo. To understand a cannibal galaxy is to understand a fundamental force of cosmic architecture, the principle that shapes the largest things we can see. These giants are not accidents, they are inevitabilities, born from the universe's relentless tendency to build up structure through attraction, merger, and yes, consumption. They teach us that the serene sky is an illusion of our brief moment in time. In the deep rhythms of the cosmos, change is the only constant, a slow, majestic, and often violent dance of construction and transformation. So the next time you find yourself beneath a clear, dark sky, look up, see not just points of light but stories. See the potential for spiral arms being stretched into streams, for quiet giants growing in the dark, for an entire universe in motion. What cosmic mystery captures your imagination? Is it the fate of our own Milky Way, the search for life on distant worlds, or the enigmatic nature of dark matter itself? Let us know in the comments below, and subscribe to join us as we continue exploring the deepest wonders of space, one story at a time.